At the end, I started by using the one big formula that we will see today again. But yesterday we arrived to one expression of the number of scattered neutrons in a given direction for a non-polarized beam has two terms: the square of the nuclear structure factor plus the square of the magnetic interaction vector modulus. And then these two terms appeared non-coupled. This was the talk that I explained yesterday, and we were using the magnetic part, and I put some example. Today, the idea is to use one polarized beam, and as a consequence, these two terms will appear, but also we will have interference terms, and we will have other effects that we will use for to the study of magnetic structures. Okay. Then this is the main goal of today's talk. After one historical introduction, I will pass to try to explain a little bit about the Bloom-Malayev equations. It's not easy, but I will try to do my best to explain how we can arrive to these expressions. And then I will say something about how we can control and polarize beams, instrumentation part, and then I will enter with examples. Maybe this will be in the second part, I don't know, in the second part of the talk, introducing the magnetic form factors and spin densities. That means the Bloom-Malayev equations will be adapted for each one of these examples: spin densities, magnetic side susceptibilities, longitudinal polarization analysis, and finally spherical neutron polarimetry. Okay. If you have questions, you can ask at any moment. We don't need to wait to the last moment if you want. Then, introduction. Yesterday we saw this man, is Chadwick. He discovered the neutron in 1932. This is the history of the neutrons and polarized neutrons. Then in 1937, Swinger here did the theory of polarization by a ferromagnet. Later, Fish do in 1938 the partial polarization for a neutron beam by passing through iron. Then Alvarez and Bloch in the 1940s determined the magnetic moment of the neutron by polarization analysis, and Otto Halper and Johnson did the theory of neutron scattering also in 1941. Later, Hughes and Burgi in 1951 did the first experiments by polarized mirrors, a proof of the magnetic dipolar interaction. Clifford Schultz and Bruchhaus, but Clifford Schultz here did in 1951 the polarizing of crystals of iron 3 oxygen 4 and cobalt, the Hausler. And then the first polarized beam of magnetic form factors on nickel and iron was determined by Natanz and company in 1959, and Blume and Sergei Malayev, who passed away 3 years ago, both the same year, and also in the same year they did the general theory of neutron polarization analysis. Also in 1969, Moon, Richter and Kohler in Oak Ridge, they did the first experiment on polarization analysis, longitudinal polarization analysis. And also, more recently, Ferenc Messier did discover or invented, if you want, the spin echo techniques by using these also polarized neutrons. And I would like to arrive to Cryopath, that it was the instrument that facilitates the control and the measure of the polarization in the beam. That was due to Francis Tasset, James Brown, and Bruce Forsyth. Francis and Bruce, as far as I know, they passed away recently, but Jane Brown, she's still alive in UK. Then with the use of polarizing neutrons is very common in a lot of areas in neutron scattering techniques, but today, you can see here, we will focus on the use of polarizing neutrons in single crystal diffraction. And this, we will not enter in the inelastic scattering, reflectometry, SANS, or spin echo. These other techniques I will not touch here today. I will focus on single crystal diffraction, which is enough for 1.5 hours. Then let's go to some mathematical, to the derivation of the Blume-Malayev equations by using, okay. Then let's remember the neutron. Professor yesterday in the first lecture explained that it's formed by 3 quarks, and the neutron is a baryon. It's an elementary particle formed by 3 quarks bound by the strong interaction. The mass of the neutron is equivalent to the mass of the proton. What is important here is the spin of the neutron, 1/2. Then with this spin, we can determine the magnetic moment of the neutron, which is this, the neutron magneton, 1/2 of the sigma matrix Pauli. And gamma here is 3 because I put here 1/2. If not, is 1. Sometimes you can see gamma over 2 around 1.8. And the nuclear magneton is much smaller than the than the Bohr magneton because it's related with the mass of the proton. Then the quantum state, important, the quantum state of the neutron is characterized by its wave vector. We saw yesterday that the incoming neutron was characterized by a plane wave with a k vector, with a momentum. And yesterday we didn't take care of this, but the neutron, we can characterize the spin of the neutron by one spinor, and that will be related with the polarization state of the neutron. Okay? Then the polarization vector of the neutron will be this value, where sigma is the Pauli matrix, is a vector of 3 matrices. And then if you put here sigma x, sigma y, and sigma z, you will obtain a vector that will be a unit vector. Then, in the beam, we have many neutrons that have different polarization states. At the beginning, we don't control the polarization state of our beam. Then let's P, the polarization vector of the beam, is the average of the polarization vectors of all the neutrons. We have a beam, and every neutron has a state, and we can define the average of the polarization for each neutron, and this will be the polarization of the beam. Then the polarization state of the beam can be described by a 2x2 density matrix, a Hermithian operator that is writing here. Okay? This symbol is the density matrix that is telling me about the polarization of the beam. Is the summa for all the neutrons in the beam of this operator, divided by the number of neutrons in the beam. If this is a matrix, a density matrix, that means that and it's Hermithian, the trace of the operator must be 1, and the polarization will be the trace of the product of the density matrix times the sigma Pauli matrices. And with these two conditions, we can end up that the only operator that fulfills both conditions is this one. The density matrix operator is 1/2 of the identity in 2x2 times P is a vector, times a scalar product, is not a scalar if you want, sigma is a vectorial operator of 3 matrices, and then we can write like this. At the end, this is a 2x2 matrix. Okay? But in this density matrix operator, we have the information about the polarization of the beam. and we will work with this. The probability, it's difficult to use this pointer. The probability of finding a neutron in the bin in some arbitrary polarization state is sigma. Then yesterday, we didn't take care about the initial polarization state of the neutrons. Today, we will take care of this. It's sigma. And then the probability of finding a neutron in an arbitrary polarization state is given by this matrix element. This operator is telling us the probability to find this sigma state in the bin. And the eigenvectors of the density matrix are the same of this, and are 1 plus and 1 minus p divided by 2. If the polarization is 0, means that the bin is not polarized and polarized. That means that all polarization states have the same probability. If there are not polarization, all the polarizations have the same probability. If the bin is polarized, that means that we have probability 1 to have this state, or probability quasi 1 to have this state or the other state. Then, yesterday I used also this expression, is the number of neutrons scattered in a given direction given by Kf with a given final energy with today I stress this point, with a final state polarization is given by this expression. The conservation of the energy, of the total system, the interaction Hamiltonian, modulus square, bracket with the final state of the neutron, final state of the system, the scattered system, initial state, and initial state of the system. And here, today we will focus on the sigma. Yesterday, the final state of polarization, we didn't take care too much. We didn't pay too much attention. Then we need to average this expression over the initial target states. The system can be, we don't know, but it's in a given initial state. The phi is the scattered the system, the wave function of the scattered system. And if we need to average, we will use the Boltzmann probability, right in here. And we need to sum over the final target states. We need to average on phi, and we need to sum on the final average state, on the final target states. And then we have also to average over the polarization state of the initial neutron. That means in this here. And the probability to have one initial polarization state is given by the density matrix of the incident bin, which is here, sandwiched with this sigma initial in both sides. Then if the polarization state is scattered, of the scattered neutron is not observed, we have to sum. This is what we did yesterday. Yesterday we didn't pay attention to the final polarization state, and then the expressions were summed on this. But today we will pay attention to this. And then this expression becomes like this. Is a summa, is the same, modulus square, but I need to average on the initial, here, on the initial target state, on the initial polarization state of our neutron, and we need to sum on the final states. And then this bar means that we will average on all the different states that we cannot control. For example, the spin of the nucleus or the isotopes, etc. All the things that we don't control are expressed with this bar here. And then, again, like I did yesterday, we can define the amplitude operator with this integral, in which I can extract the wave plane of the neutron incident and final. They appear here in this part, and I can, all the other coordinates are in this Hamiltonian integral, and this defines the amplitude operator. It's the same that we did yesterday. Okay? Which is a matrix because now our, here, this final, sigma final and sigma initial are spinors, are spinors of two components. Then, which is a matrix in the neutron spin degrees of freedom and an operator in the Hilbert space of the target. It has dimension of a length. Yes. And then the expression becomes like this. Here is one part, this is the other, one times the other is the modulus to the square, the conservation of the energy, and the average. But here we see that the polarizations we are keeping, and we will use. Then some manipulation. The delta of energy, the conservation of the energy can be expressed like this. We will use this because by doing this, I will introduce the time dependence of the operators via of the wave functions and then of the operators via this expression. And also the average of a given operator is the probability of the state sandwiched with the states summa for all the states. Then, if I do like this, the delta, I introduce here the delta, and the fact that if you see here, I have only frequency time. The final energy and initial energy are included here in 0 and time, because these two exponentials applied to the operator is like if I pass from the Heisenberg, I pass to the vision that the operator is evolving with the time and not the wave function. It's the same. And it appears the conjugate at time 0 and the same operator at a given time, sandwiched between final and initial polarization states, and sum for the initial averaged for the initial polarization states of the neutron. All of these are in the document that I upload for the materials for the students. And also, of course, in Lopsy and Squires and all these classical books, you can find the same information. And then this sum of first, this is the projector, the operator that is projecting the polarization in a given final state. This is writing here, and this summa and this state and this state becomes the density matrix of the initial neutron beam here. And the other things are the same. The integral, the trace, this summa times this is the trace, and here the projector. Okay, this is the projector onto the neutron final state, and also the summa of all the projectors is the identity. This is a trick that we use in this, not we, everyone use, that we can say the correlation function between two operators, 0 and t, integrated by the energy with the energy like this, we express in this way. This is to reduce the use of too much symbols. And with this, we end up with this very short expression, but with a very condensed expression. Kf, Ki, initial momentum, final momentum of the neutron, trace of this correlation of two operators with the projection of the operator in a given final state, and the density matrix of the incident beam. And nu is because we are doing this kind of integral. every time that you are observing here nu or omega, here I don't know if I told you yesterday that I'm using crystallographic notation. That means that I will use frequency and I will use the 2 pi in the exponentials. Many times 2 pi nu is omega and people use omega t, and here they put omega. But we keep the 2 pi every time. Okay, then with this expression, you can go a little bit further and you can determine the intensity of the scattering beam. Here we have omega. That means that it includes elastic and inelastic. For the moment, omega is there. That means that there can be change in the energy, exchange in the energy between a neutron and system. And the energy of the intensity of scattered neutrons in a given direction with a given energy is this expression here. The amplitude operator, complex conjugate, and here we see the density matrix of the incident neutron beam. And is the polarization vector of the scattering beam is how we can define. If you remember, we define the polarization as the probability to find one neutron in a given polarization. That means that this is the number of neutrons is here, the total number of scattered neutrons. And if I put here sigma x is the projector that I define here. If this corresponds to sigma x, sigma y, or sigma z, I will have the probability to find the neutron in this or this or this state. If I divide the number of scattered neutrons in this state divided by the total number of neutrons is giving me the probability to find the neutron in that state. That means that the polarization of the beam is precisely this quantity. Also, if we here, if we do this integral, these integrals, the integral of the correlation function in between these two operators can be done by using what we are doing is we do the integral minus the elastic part plus the elastic part. And the elastic part is precisely the correlation, the two operators appear out of the correlation function, like this. And this is the elastic scattered beam. That means here the number of neutrons scattered in a given direction. Here you can see that Kf and Ki are the same, then don't appear here, and then is the same expression. But the big correlation between the two operators appear decoupled. And I have here the total number of scattered neutrons is summa for all the final states of this function. But here you can also, if doing the same, the polarization vector of the final state will be 1 over the total number of scattered neutrons of this trace. And you can see here, identify rapidly that this quantity here, AQ, rho I, and A plus Q, is divided by intensity, is precisely the density matrix of the final polarized, of the final beam, of the scattering beam. And then now, once we have this expression for the final polarization and for the final scattered intensity, we need to come back to the amplitude operator. And yesterday we used only the nuclear part. The nuclear part is this part that is related with the amplitude, with the scattering length, plus this part that we didn't consider yesterday, and today neither, and the magnetic part, which is here. Do you remember the magnetic part of the interaction was related with the with this operator that we call magnetic interaction vector operator. Then, this, the momentum of the nuclei and the magnetism in your system are coupled with the spin density, with the matrix, Pauli matrices, and the other part, we put here the identity in 2 by 2, is the scattering length, basically. But now we will use the amplitude of, we will use both interactions at the same time. And we will introduce these two terms here and here. And this will produce the Blume-Malayev equations. It's very, I understand that it's not easy. You need to study this in the papers to follow better, but in 1.5 hours we cannot do better. Me, at least. Okay, then, but you see here, the amplitude operator, there are both terms. And this, if we trade together both terms, we will obtain interference between one term and the other. And this is what happened by working with this expression. We arrive to the first Blume-Malayev equation, which is the total scattered intensity in a given direction labeled with the scattering vector is the square, the modulus to the square of the nuclear structure factor, which is written here, the modulus to the square of the magnetic interaction vector, modulus to the square. This we have yesterday. But today, because we are considering the polarization of the beam, we are considering that our beam has one initial polarization, we obtain the interference vector here, which is a vector that contains the nuclear structure factor and the magnetic interaction vector together. Then this is one vector plus his complex conjugate. That means that this is 2 times the real part of the vector. Times the polarization, of course. If the polarization is 0, then this term doesn't appear, and we end up with the expression that we had yesterday. Yesterday, we were not considering polarization, then this will not appear. This doesn't appear, did not appear. And we have here something that is very interesting. This is a chiral vector. Chiral vector is something due to the non-collinearity of the magnetic structure. This non-collinearity will produce the chiral vector. The chiral vector appears also multiplied by the polarization of the initial of the beam, of the initial beam. And then this nuclear magnetic interference vector, we can define this vector like this with a real part and one imaginary part. But one vector plus his complex conjugate is 2 times the real part. That means that this will be this part of the vector. Okay? I follow for this notes taken from Juan. I don't know where you take this note, but I was inspired in your notes. Okay, and then the final polarization of the beam multiplied by the intensity. You can divide if you want, but many times you will see like this. It is like this, is the initial polarization multiplying the difference between the modulus to the square of the nuclear structure factor and magnetic interaction vector. Okay, it depends on the initial polarization. Something also that depends on the initial polarization, here, this scalar product times this vector. This is a vector. Also, this term depends on the initial polarization. Also, this one. But you can see here that there are something that doesn't depend on the initial polarization. That means that depending on how is the magnetic structure, we can have a final polarization even if the initial beam was not polarized. And we can write this expression, the final polarization, like a matrix multiplying the initial polarization plus something that doesn't depend on the initial polarization. This P is these 2 terms, and this matrix is what we have in front of the initial polarization. We can work a little bit on this. Also, this is coming from your notes. And we have this expression for the matrix and for the vector. This vector is here. And the vector finally is 1 over the total intensity, scattering intensity of the real part of the interference nuclear magnetic interference vector minus the chiral vector. And then this will appear in the diagonal term of one matrix 3 by 3. This will appear, this is a symmetric term that will appear in both sides of the diagonal, but with the same sign, and this will appear this is antisymmetric term, will appear also in both sides, but changing the sign. And then what people do usually to simplify this vector equation, we use the lower reference frame, and we choose every time x along the scattering vector. And then z is the vertical one, and y is the vector that completes the 100 Cartesian system. But by choosing x along the scattering vector, we arrive that the magnetic interaction vector will not have x component, because it's every time perpendicular to the scattering vector. And then the final expression for the scattered intensity in a given direction q, blah, 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 is the one term, that is the nuclear structure factor to the square, the magnetic interaction vector modulus to the square, plus, by choosing this system, the chiral term has only x component times the polarization along x, the real part y component, this is a real vector, y component polarization initial along y, and the real part z, polarization along z. This is for the intensity. Here you can see the chiral term and the interference vectors. And by manipulating all these expressions, you will see that the final polarization, a vector of 3 components, is 1 over the total scattered intensity and this matrix times the initial polarization plus something that depends on the chiral and the interference vectors. Then here we define this quantity is this. It appears here and there. Okay? It seems complicated, but at the end is not so. One can become familiar with this expression. Also, we can define this polarization matrix, which is each column represent the polarization along x, y, and z, and the components x, y, and z. That means that we send neutrons polarized in x, and we measure in x, y, and z. We send neutrons polarized along y, and we measure along x, y, and z, and so on. And then we can build this kind of matrix that is where we have many terms that depend on the magnetic structure. This term that we have here, we need to measure and have the information of how the magnetic moments are located in your system. Okay. Then also, for a pure nuclear reflection, that means if it is purely nuclear, there are not interference, there are no magnetic scattering, and then all the intensity is nuclear. Then the final polarization matrix is the identity, no change in the polarization. You can go to this. You can go, sorry. you can go here, and you can see that the final polarization will have 1, 1, 1. If it is purely magnetic, then the nuclear intensity will be 0. If it is purely magnetic, no interference there, but we can have chiral term here, and the expression becomes like this. And what we can see here is that you can see -1 here is telling me that the first column, the polarization of the scattering vector is inverted. Because remember, we put the scattering vector along X. And this -1 here is telling me that the polarization along X is changing the sign, this -1. And if we take out the chiral term, these two terms here, this will be 0, this will be 0, and then I will have this very short, this simple matrix polarization. Something about instrumentation. I don't know how much time. Okay, then. Yes. I will finish the instrumentation, and then we will do a short break, and after the short break, we will continue with the examples. Okay, then we derivate the Bloom-Malayev equations, but there is something very important. We need to know how to control the polarization in our beam and how to measure the polarization in our beam. This is very important also. And then I prepare some slides to explain this. This is the first experiment of Monrist and Kohler in '69, and you can see here many different devices. This is our sample, and here we have our initial neutron beam that is not polarized. We can use one polarizer. Later I will describe how to polarize. Then this polarized, only the red neutrons are passing, you can see here, and a flipper that if it is off, that it do nothing, that means the same neutrons pass. Then 5 red neutrons arrive to the sample. We can put or not one magnetic field here if you want. And there are scattering processes in the sample. Some of them are flipped. If they are flipped, it's because there are something magnetic in our sample. And then one flipper, a second flipper that is off, that means that do nothing, the same neutrons pass, and one analyzer that only allows the pass of the red neutrons, and one detector. If this kind of setup will measure one non-spin flip process. That means that I start with here with a spin up, and I will measure a spin up. However, if I change this flipper and I put on, that means that it will flip. I will start now. The sample is not anymore spin up. At the sample are arriving neutrons with a spin down. And we are measuring neutrons with a spin up, like this, on, off. And we can do like this. If this is off, the sample will receive neutrons with a spin up, and the detector will receive neutrons with a spin down. These are called two spin flip processes here. And if I put on, the sample will receive neutrons spin down, and the detector will receive neutrons spin down. And this, by using one polarizer here and one analyzer also here in front of the detector, and by using two flippers, I can choose the different states of polarization, plus and or minus, up and down. This is a very simple experiment in which I can change polarization only up and down. But later I will show you that also we can measure the polarization vector in any direction. Then, yes.
After the analyzer, the position of the spin is changed. Is there meaning, the special meaning? You see after the analyzer.
The analyzer only allows the pass of a given polarization.
Yeah, I noticed the spin, the position is you change the red arrow, right?
Sorry, I don't.
The position of the red arrow is changed before the analyzer and after analyzer. Is a meaning of that?
Here,
yeah.
The idea is that here we have let's say five neutrons, two of them with a spin up, and the analyzer only allows the pass of the spin up neutrons.
Okay, so the position is the relative position is no meaning of the.
No meaning.
Okay.
This is just a cartoon. Okay, then non-spin flip here and spin flip. Okay, then now I will pass to describe how we can polarize, how we can flipper our sample. Then, the first element, the polarizers. We have at least three different manners to polarize the beam by using filters, for example, by using the preferential absorption of polarized helium-3 nuclei, which has advantage and disadvantage. We can also use polarized mirrors or supermirrors using preferential reflections, or we can use polarizing crystals, like Heusler crystals, in which we can see that what is happening, that nuclear structure factor can be matched with the magnetic structure factor, and then we can see that there are crystals that allow the diffraction of one polarization and not in the other. Then, polarizing filters. The idea is to use helium-3 to polarize the nuclei of helium-3, and then when you send the neutrons with helium-3, half of the neutrons are absorbed, and the other part pass and is polarized. Here we need to play between the polarization state and the absorption, and then people define a kind of parameter that is relative nucleus transmission, and which is also important, the rate of polarization, how we can polarize our beam. And this kind of objects with helium-3, you can see you can cover a large solid angle, and but you need also auxiliary equipment to polarize all these helium-3 nuclei. And also the polarization decay a little bit with time. You need to take care of this also when you are doing experiments. The other idea to polarize is the use of polarizing mirrors. You know, the neutron, like the photons, we can define a refractive index for neutrons, which the refractive index will depend on the scattering length and also on something related with the magnetic part in your sample, because the neutron is interacting with nuclei via scattering length and with magnetic moments via something that I call here P. And then the same that you for photons, the photon is interacting with electronic cloud, and we use the electric constant, which is related with the polarizability of the nuclei, and with the electric constant, the square root, we produce the refractive index for photons. Doing something similar, but not with the electric constant, but with a similar quantity, which is the scattering length and the magnetic part, we can build this kind of refraction index for one polarization or the other polarization. This will change here. And then by using this, we can go and apply the optical that we study in physics, the total reflection coming from optica and the Breussler angle, all these concepts, and we can see that there is an angle for neutrons by using this refractive index for which only one polarization will be reflected in the mirror. And then also we can build, with this idea, we can build B-layers or multi-layers, one layer that is not magnetic and one layer that is magnetic, and then we can measure, we can determine the reflectivity of this B-layer, or we can do multi-layers. And then if we do, okay, before this, and then at the end, also we can have, if we want to ensure that our mirror is polarizing, that there are some neutron that is fulfilling this condition of polarization, we can bend a little bit the mirrors. This is the idea of the polarized, of the analyzers in the diffusion, in the several instruments at ILL and in other sources. This was developed by Otto Schan. But then, like this, we can polarize by using one mirror. But many times we use a kind, not a bilayer, but a multi-layer system for which we can optimize the reflection for different range of wavelengths. Because this is good for one wavelength, but we need to have polarization for many wavelengths. And then we can have, like this, mirrors that, you can see here, that reflects one given polarization and not the others. And this kind of mirrors we call super mirrors. Okay. Okay, then you can see here the reflectivity for a given polarization, up and down. One is going to 0 and the other one is reflected. And then as a consequence, the polarization is good in a very large range of Q. This is one image of the Bender analyzer in D7, the diffuse scattering instrument, and these are the bended mirrors that I explained you. These are in front of the detector. Then, also, we can polarize the crystal by using Heusler or one monochromator that is polarizing the beam. Then we enter with a non-polarized beam with up and down all the polarizations here, all the states, and only the reflected one contains one polarization. What is, if we use this setup, we can use also, if we want, magnetic field to increase the magnetization of the components in the monochromator, but with this setup, the interaction vector is directly the magnetic structure factor. And then you can go to the intensity reflected, diffracted, this direction, and has this is like this. And you can take what is happening when polarization is 0 here, and you will see that here we have this plus minus here. And then if I arrive to have the same magnetic structure factor than the nuclear structure, magnetic structure factor, the same that the nuclear one, modulus, then I will see that one of the intensities here is 0, because if this is equal to this is 0. And then I will use, this is one way to obtain polarized beams. You can see here this table, different materials, by using different reflections for which we obtain that nuclear structure factor and magnetic structure factor are similar, and then we can use as polarized crystals. Then how we can guide the polarization? Then here I want to explain two concepts. The adiabatic rotation of the polarization, that means that every time we can say that if we move slowly the polarization, we are every time in equilibrium. And then how we can do this? We can use the polarization will follow one magnetic field if the magnetic field is moving, is changing slowly, smoothly, like this. Then this is called adiabatic rotation. And this is related with the fact that polarization will proceed along the magnetic field, and also due to the energy of the neutron, it will have a Larmor frequency. And then the polarization will follow the magnetic field. Here, if we change magnetic field slowly, polarization, you can see here from the vertical to the perpendicular, and then polarization is moving smoothly along the magnetic field. And it depends on the energy of the neutron, on the magnetic field, etc. It's around, 2.6 degrees per centimeter by millitesla and angstrom. Okay? Then the field is not necessary that the field is high or not. With 10 Gauss is enough to move the things. But what happens if we have non-adiabatic rotations? That means if I change drastically the magnetic field from one direction to the other, then let's say the polarization don't have time to go to the other direction, but start to change the precession. Here, the polarization was doing a kind of precession along B pointing up. If I change the magnetic field rapidly to the other direction, polarization will change in the other sense, like this. Or, if you want also, I can change rapidly the magnetic field from one direction to the other, and then the polarization, the rotation of the precession will immediately be adapted to the new magnetic field. Okay? This is not the polarization in total that is changing, but it's changing we use the change of the precession here. And like this, by playing with these two concepts, you can do something much more complex, like this message pi filter, in which you play with this. This is non-adiabatic, but you change subtly the magnetic field, and then the polarization, if you measure correctly, will adapt to the new state. At the end, we can play with the polarization by using small magnetic fields. And then I will stop here, 5 minutes, and we will continue later, before the examples. Okay? 5 minutes, break. Thank you. Magnetic side susceptibilities, longitudinal some quantity by using this technique of longitudinal polarization analysis or spherical neutron polarimetry. To determine, for example, here we will see that there are magnetic structures that only can be determined by using this technique. This is one special case of this one, but sometimes it's enough to determine many things. Magnetic side susceptibilities and spin densities is only using the fact of the first Malayev equation. Here is the second one. Okay. Spin densities and four factors. Then, which is the idea of the determination of the spin densities? You know, at the end we want to determine which is the orbital or the space that our magnetic electron, that is not pair, is unpaired electron, is occupying in the space. And this orbital, the Fourier transform of this orbital is directly the magnetic form factor. And we can also, this magnetic form factor, we can determine directly the orbital in which the electron is moving and is producing the scattering. But for this we will use polarized neutrons, but we will pay attention only to the scattered intensity. We don't take care here about the state of the final polarization. That means we will polarize our neutron beam with a polarization parallel to one given direction, for example, parallel to the magnetic field, which is vertical. We will enter with this polarization, and we will measure the flipping ratio. That means the ratio between the one scattered intensity in one bright line up, with the polarization up, and with the polarization down. Then, that means we will use this expression of the the first equation of the Blume-Malayev, in which we have the nuclear structure factor to the square, the magnetic interaction vector modulus square, the interaction vector, the interference vector times the polarization, and the chiral term. And here we are using the fact that this quantity, you will see later, is employed to magnify small magnetic form factors, magnetic structure factors. And here, the initial polarization is parallel to the zeta prime. That means here we have one scattering vector, this is X, we have Z, which is, and Y. And if the scattering vector is not in the horizontal plane, that means that Z is not in the vertical. For that reason, I define Z prime. You will see later. And here, I can determine the intensity for neutrons in a given polarization up and down. I will obtain this, and here, polarization is going up and down. That means that appears here. But polarization is parallel to this vector, to this direction, to the zeta prime direction, parallel to the magnetic field and parallel to the magnetization, because we usually put a magnetic field to polarize our sample. Then I need to project this vector here to the zeta prime direction. And also the chiral vector I need to project to the projected to the initial polarization, which is parallel to zeta prime. And then the flipping ratio is intensity plus divided intensity minus, up and down. We will have this expression. That means that, let me show you before this scheme. Imagine we have this scattering vector. We want to measure the scattered intensity along Q, the red one, with plus and minus. Then, if I use the Blume-Malayev equations, I need to use in the Blume-Malayev equation this red part. This red part is coming from here. Here. Sorry, red no. I need green part. Green part. Okay? Then if I apply a magnetic field along zeta prime, the polarization is along zeta prime, the magnetic moments, the magnetization in my sample will be parallel to the zeta prime, and this will be, the magnetic structure factor will be parallel to the zeta prime also. And then what is entering in the scattering is the magnetic interaction vector, which is the perpendicular component of the blue vector to the red one. That is the pink here. Okay? And this is MQ sinus alpha. Alpha is this angle. But what is entering in the equation here is the green. Then I need to project again to the blue one, and then it appears another sinus alpha here. Okay? And then by using this, I put in the expression of the flipping ratio, and I will end up with this expression here. That means that if I have a good knowledge of the nuclear structure, that, for example, I can measure the nuclear structure in one experiment without polarized neutrons, I can go back by measuring the flipping ratio. I can go back and I can extract the magnetic structure factors, because the polarization I know, and this I know. N is well known. There are some problems. If the structure is centrosymmetric, then it's very easy. It's easy. If not, we can also work with this expression, but it's a little bit more complicated. Then the knowledge of the nuclear structure factor allows the determination of the magnetic structure factors, which at the end, the magnetic structure factor will give us the information about the spin density or about the magnetic form factors. Then here, the only thing is that we need to polarize our beam parallel to the vertical direction in which, for example, in which we will put the magnetic field, and by using the flipping ratio, we can determine this. This is interesting because the use of polarized neutrons is interesting because if you imagine that your magnetic structure factor is 0.1 times the nuclear structure factor. Imagine that it's very small and is like this. And then with this technique, if we don't use polarized neutrons, you can see that the intensity diffracted due to the magnetic part is only 0.01 times the intensity that I have before. Then it's difficult to measure this small quantity. However, if we use polarized neutrons for one intensity or the other intensity, the fact that we have the interference term here amplify the effect of the magnetic part. You can see here in one case and in the other. And then the flipping ratio is the quotient of this, the ratio of this. And then his technique allows very precise measurement of the weak amplitudes and is used to determine the magnetic force factor and magnetization distribution maps, what I call spin densities. It works in paramagnets in which the idea is that you need to control the magnetic structure factor in your sample. And the magnetic structure factor, you need the best is to have the highest magnetic structure factor. If you use an antiferro, it's better don't use this technique in the antiferromagnetic state, but in the paramagnetic state. If you have a ferromagnetic sample, then no problem. Depending on the anisotropy of your material, at the end you need to control that the magnetic structure factor must be aligned as much as possible with your magnetic field. And only magnetic structures with K equal to 0. So, this is difficult to control like this. Okay. K equal to 0 because this technique is exploiting the fact that the interference term, if we have K different to 0, that means that the magnetic signal will not be appearing at the same point that the nuclear one. And then we cannot have this, we cannot use this term. Also, if we have, I forgot to tell you that here you can see that we don't have any chiral term. Wait a moment. The chiral term is not appearing in this expression. If we have chiral term, we cannot use this expression here. For that reason, is absence of any chiral term and magnetization aligned with the applied magnetic field in the vertical direction. Then MQ are the Fourier components of the total magnetization distribution in the direct space. Remember, this expression of the magnetic structure factor in dipolar approximation is the sum for all the atoms in the unit cell of the magnetic form factor times the magnetic direction for every atom times the phase. And this is the integral in the cell of this distribution. That means that the magnetization can be, the spin density can be extracted from the precise measurement of the magnetic structure factors here. Then, with the flipping ratio method, we can arrive here. If we know precisely the nuclear structure factor, we can determine this one. And to determine this one, there are we can determine directly by using direct methods, for example, by using Fourier inversion or maximum entropy. With Fourier inversion, we will have truncation effect. That means that we will not be able to measure one infinity number of Qs. That means that at the end, this summa will have truncation effects, and is restricted to centric cases, in which it's easy to determine this, because if not, we have the phase problem. And with maximum entropy methods, it provides the less informative map consistent with your observations. Then I will show you one example of this. Here, in manganese oxide and yttrium, barium, copper, oxygen 7, by doing Fourier, they measure, these people here, measure the flipping ratio, and by doing Fourier inversion, they reconstruct the density maps, where is the magnetic electron all around the atom, by doing Fourier inversion and maximum entropy technique. You can see that this maximum entropy many times produce better results. But the main fact, both techniques are producing. This is a little bit more here with more effects, and here is more clear. Also for the other compound, with Fourier inversion and with maximum entropy. Here clearly maximum entropy is producing better results than Fourier inversion. This is another in my side, in molecular magnetism. Also Robinson and company with James Brown did the spin density maps of this very well-known manganese 12 single molecule magnet, in which we have 3 different manganese, 1 here and 2 there, and that these 3 different non-equivalent manganese will reproduce all the 12, all the others. And then with spin density, with flipping ratio technique, they determine that the manganese in the inner part here, in the tetrahedra here, are coupled antiferromagnetically to the manganese in the outer corona, outer shell here. Okay? That means that this molecule is a kind of ferrimagnetic molecule. This is not ordered, but the spin density in M1 points in the opposite direction that the spin density at M2 and M3. Here is M1, M2, and M3. And the data are very consistent with the theory. This is another example that we did at ILA long time ago. Here I can tell you too much things, but we were interested. I will introduce this compound because it will appear later in other examples with ammonium here. But this compound was studied in our group since long time ago. We did many experiments with Juan, not me, my boss. Many experiments with you in the 80s, maybe, or the 90s. But these experiments were not treated. Okay, but we determined, Juan, Merchegabas, and others determined the magnetic structure of the material, which is like this. Is ferromagnetic planes coupled antiferromagnetically along the B direction. But what was interesting here is these compounds, is pentahalide, aqua pentahalide, iron with alkaline material. These compounds have Néel ordering temperatures very large if we compare with other similar compounds with similar exchange pathways, with similar distances. However, in the iron compounds with chlorine, bromine, rubidium, or potassium, the ordering temperatures are 1 order of magnitude larger. And then we thought why this is happening, and we say, okay, maybe it's because there are some spin delocalization from the iron to the exchange pathway. And then we did experiments to measure this spin delocalization. And this experiment I show here you, we treat with maximum entropy, and you can see here the first analysis for potassium and rubidium. We can see the main spin density is located at the iron, but we observe some spin density delocalized through the halogens here. This is done with with non-prior spin density initially. That means that in maximum entropy, you can start from nothing, non-prior spin density, or you can say, let's start assuming that iron have 5 Bohr magnetons. And then if you start with this other assumption, then you will obtain something different, but it's very similar, but with more precision. And you can see that, in fact, it seems that this direction that connect via the most important interaction exchange constant, there are a kind of delocalization. And there are more to the halogens, more than oxygen, and more in bromide than in chlorine. But at the end, you can see that the iron is delocalizing more or less 10% of the 1 Bohr magneton is going from iron to the halogen and the oxygens, or to the, here also the same, more or less, 19 and 21%. And then maybe this is the reason why this system orders at higher temperature than other similar compounds like this one. This one also, people did spin densities, and the delocalization was very, very small. Okay, this is one example. This was maximum entropy and Fourier direct methods. We can use parameterized models. That means indirect methods, in which what we are doing, we are modeling the spin density by using, in one side, magnetic wave function. That means the magnetic orbital, and then the spin density will be the summa for all the atoms, one population for each atom, and this projection, modulus to the square, where phi, you can see here, are the atomic magnetic wave functions, which is a linear combination. The coefficients must be modulus 1 of the standard atomic orbitals. Okay? Then here, by fitting these parameters and this one here, we can calculate, we can model this, and we can calculate with this theoretical expression the flipping ratio. And then we can fit with the experimental one by moving these parameters. And this is done with full prof. It's done these kind of things. You can do easily. Okay, then one example of this. The other method is the multipolar expansion approach. Here, you are modeling directly the spin density. You are not modeling the atomic wave function, magnetic wave function that will produce this magnetic density, but you are modeling directly with real spherical harmonics the spin density. And then you have your spin density, and every time you can put in the base of the real spherical harmonics. This is a base, and then you can every time decompose this in the harmonics. And then you will, again, in full prof, you can play with this multipolar expansion approach, and the fitting parameters will be these populations, and also the exponents, some exponents here that is telling you the contraction of the orbital. Okay, one example of this is, for example, these are another molecular compound. In this case, the beta phase of the paracyano perfluoroaryl dithiodiazolyl compound. This is a molecular compound, a purely organic magnet that orders at 36 Kelvin. And we have other similar compounds with the similar molecule, which is the magnetic moment, that don't order. Then we were interested to see the spin density in this molecule to understand why one compound is ordering and why the others are not ordering. This order, but a very low temperature. And then, of course, the substituent in the para position will control the packing of the crystal. But here, this was the idea, okay, in the example, and we use polarized neutrons to determine the spin density here and to understand how one molecule is coupling with the others. Methodology. The first step is to go to D9 or one short wavelength hot neutron, short wavelength neutron diffractometer, single crystal, because we need to have a good determination of our nuclear structure. And for this, we need to go far in Q. We need to this kind of instruments. And then you will be able to determine with high precision the molecule and the hydrogens or the deuterium, etc. Okay, then this will give you the nuclear structure factors that will be employed in the next. You can, after this, you can go to D3 or another similar instrument in which you can measure the flipping ratio, and with the flipping ratio, you can determine the spin density. And in this case, the spin density is like this. Also, you can, I don't know what is happening there, but you can do you can determine where the electrons are that with X-ray crystallography, and this was the figure. I don't know what is not appearing. You can do also ab initio calculations, but the crucial point is the experiment, because ab initio without the experiment is nothing. Experiment is telling you that your ab initio calculations are correct. And once you have all this information, you can understand, for example, why these two molecules are interacting ferromagnetically, because the overlapping between the magnetic wave functions is zero. That means that here this favors the ferromagnetic interaction. Okay? And this was done in this molecule. Here you can see the different models by using these magnetic orbitals for nitrogen, sulfur, or carbon. And you can see here the magnetic part is here, the projection on the plane, and the vision from the back. You can see here the pi form with one model, and you extract how much magnetic moment is in every atom. You can complicate a little bit the model by using more orbitals, or even hybridization for the nitrogen, and you can extract the quantity of each. This must be normalized for every atom and the population. Okay, or the spin density by using the multipolar expansion approach. Different models by using different dipoles. Yeah? It's the same. Okay, this is one example of how to use polarized neutrons to determine magnetic spin densities. With all this information, you can understand also in this compound that these two molecules are located like this, and this will produce also a ferromagnetic interaction because the overlapping is zero. Also, in the previous compound, you can use parameterized models to determine the same that we determine with spin densities. We also, with this flipping ratio technique, you can go and model the magnetic form factors of every atom in dipolar approximation. This is the expression, and here we have the Bessel functions and the Fourier transform of the radial part, and this is what is entering here. And you can see, for example, for manganese with the dipolar fit observed and calculated, and for here the agreement is not so good because the dipolar approximation maybe is not the best for cobalt, which is a little bit anisotropic. Okay? But this is the way to measure the form factor. Also, sometimes you cannot orientate the magnetization along the magnetic field because your system is anisotropic. Then, even like this, you can determine some information that is very useful. This was developed by Arsène Gukasov and James Brown. And the idea here is, okay, I cannot polarize my magnetization, but I can tell you that my magnetization respect to my magnetic field is related by a susceptibility tensor. And then I will model the components of the susceptibility tensor. This is the idea. Maybe I need to go faster. And then by modeling these components here, they can, by using the same flipping ratio technique, by using this, the magnetic moment is expressed like this, and the fitted components are the susceptibility, the fitted parameters are there. And this is useful when you have this kind of systems. And for example, they use this technique to differentiate between this for uranium, aluminium, silicium. They were not able to distinguish which was the magnetic structure in one side and in the other, but however, they measure the susceptibility, magnetic susceptibility tensors as function of temperature, and when the system is decreasing temperature before it arrives to the ordering, they determine a strong anisotropy of these tensors along these directions. And then this is a proof that the final or magnetic ordering is like this one. Okay, let's go to explain something about XYZ polarization, longitudinal polarization analysis. Remember, this expression I introduced before is the final polarization, 1 over the total intensity, this big matrix, initial polarization, plus something independent. Here the idea is I will put here polarization along X, 1, 0, 0, Y, 0, 1, 0, Z, 0, 0, 1, and I will obtain a vector that I will project. The vector final will be projected along X, Y, and Z. Because at the beginning, people was able only to measure, to polarize in one direction and to measure in that direction for the 3 directions. And then for polarization along X, they can measure up and up, up, down, down, up and down, and down and up. And then the sigma X up, up is telling you the nuclear part. The sigma minus, the nuclear part. Of course, if there are not a spin flip, we are also observing the nuclear part. If there are a spin flip, we observe the magnetic part also. And for Y, we have this, and for Z, we have this. And then, okay, this I thought. By using this, you can immediately see that by measuring the non-spin flip components, I have direct access to the nuclear part, or by combination of these scattering cross-sections, I can obtain the different components of the polarization matrix. Okay? Also, we can use, here I am using the initial polarized vector, but I can use non-polarized vectors, and directly the chiral vector will produce polarization. And then this is what we did, for example, here. I will go faster. In this example, with Kosaka-san, no? We were interested in this compound, cesium chlorine, for triangular lattices that in one direction are rotating, forming a kind of helical structure. And they were interested to produce homochiral crystals, because the crystal, if you grow like this, have different chirality domains, nuclear chirality domains, and every chirality domain, nuclear one, will produce one magnetic chirality. And then they were able to produce only crystals with one nuclear chirality. And they wanted to measure the magnetic chirality. That means they wanted to extract the chiral term here. Here. The chiral term. And then the chiral term is directly, you need to measure the polarization along X plus, minus, minus, plus in the crystal. And then they did the one satellite. They measure the intensity plus, minus, minus, plus, you can see. And then they observed that only one was visible, or by taking one kind of crystals, only one magnetic chirality appears. In one satellite, only one. And in the other, the contrary. And that means that every satellite has the different chirality. And in the other crystal, the chirality changes. This was a proof of the chiral term and the homochirality in this kind of crystals. I will go to the spherical neutron polarimetry. Here, we control the initial state, the initial polarization state, and the final polarization state. Maybe it's better to see here the video of cryopad, of one instrument for which we can control which is the polarization at the beginning and at the end. And in this area, the magnetic field is zero in order to avoid any change of the polarization after the interaction with the sample. Okay? That means that we are able to control, to put polarization in one direction and to measure polarization in a cross direction. That means that it allows to measure DXY or other cross components. This is a cryopad in D3 at ILL. Also, there are some replica of this instrument in other sources, but here they were the first one. And for example, this was very important, this technique, because all of these magnetic structures are producing exactly the same intensity and polarized in the diagonal terms of the polarization. That means that the only way to distinguish between this magnetic structure is to measure the non-diagonal terms of the polarization matrix. That means this is one example. I will skip this one, and I will go back to this compound. Because this is the initial compound that I explained you before. We have good crystals, but this compound with ammonium shows multiferroicity below 6.9 Kelvin. And for example, I can show you here the magnetic structure is forming cycloids that are coupled 2 by 2 like this, and also the propagation vector is along the z-axis, that is along this direction, and you can see by changing magnetic field, you can change the magnetic structure like this in the compound, but there were several things that we didn't understand, and for that reason, we went to cryopad to solve the problem. And then the first question was, what is happening in the order, which is the magnetic space group in the ordered phase at low temperatures here, and also which is the symmetry in this very narrow region for which was impossible to determine the magnetic structure. This narrow region is 0.02 Kelvin. It's very difficult to see anything here. But with cryopath, it was possible to determine the magnetic structure here. Then, which is the symmetry for, we know that till 6.9, the system has this space group with no polarization. Then, at low temperature, we can have one of these space group, but the only that allows polarization with 2 components or 3 components are these groups. And then we need to, by doing this experiment with cryopath, to see which is the best space group in the low temperature phase. And also, what is happening there, it is a sinusoidal phase pointing along A or along C. Sinusoidal phase because in similar compounds, not similar, but in multiferroicity, the same type compounds, the previous phase to the multiferroic phase is a kind of sinusoidal phase. But here, we suspected that sinusoidal phase was appearing here, but we didn't know it was along A or along C. It was clear that it was along A because all the family orders, the A axis is the easy axis. But was needed to measure. No, ordinary. And then here, what is happening in the compound is that we have magnetic domains with one chirality and with the other chirality. And then the multiferroicity will appear when you will have only one domain. And then you can have only one domain. If you apply one electrical field, for example, you can move this barrier and you can promote only one magnetic polarization. And then this was done, you will see the experiments, because the cross term here, Yx, is telling you the population of one domain respect to the other. And also, to measure the intermediate phase, we need to go directly to the diagonal term in the polarization matrix. And then Alberto and company measured the big crystal with electrical field in cryopath. They apply electrical field, and they measure these terms in the polarization matrix. The diagonal terms plus the cross term, one and the other, okay? With zero field and with field, as function of the temperature. You can see here the different terms. In this area, we are in the very narrow area, and here we are in the ordered area. The analysis of this is telling you that at 7 Kelvin, in the very narrow area, the system is ordering along A direction. Because the model, you can model, and the ZZ, you can see here, the experiments in orange are in agreement with the magnetic moment sinusoidally ordered along A. And for zero magnetic field, you can see here, there are nothing, but by increasing the electrical field, you can increase the Pyx in one case or in the other. And by using this, you can do even, okay, this is the magnetic structure in the very narrow area, is sinusoidally first propagating along C, and then it appears the perpendicular component. And what is very interesting is this one. By changing the electrical field, they are moving the population of each domain, of each cycloid domains, these domains here. This barrier is moving in one direction or in the other, is because this is proportional. this parameter as function of the electrical field. And this is a proof that the system is multiferroid, because with electrical field you are changing the magnetic properties. And again, as I told you yesterday, and with this, I thank you for your attention.
Thank you for Professor Campo. He gave us a very exciting, beautiful lecture. I believe.
Thank you.
I believe the polarized neutron beam is very, very useful for us to study the magnetic structure and the magnetic exciting. And I think will you be here for 3 days?
For tomorrow. Tomorrow I'm leaving.
For tomorrow. Oh.
But I will come back.
And I think we are very glad to with you to answer your question and discuss more about the polarized being used. Okay. Now we have a question right now or after. In this afternoon, we have a question time. You're welcome.
Yes,
I think
yes,
you're
yes,
welcome
yes.
to ask and discuss with you.
Yes, yes, yes.
And now, 2 questions.
Maybe in the coffee.
Oh, okay.
Students approach, when I'm alone, they approach. Here they are shy and they don't approach.
Okay. Now, we
Questions?
can end the question after in the afternoon, right?
Or in the coffee?
Yeah, in the coffee, right. So now have a coffee time.
So we will have tea break right now. I think it might be better if we start the next session at maybe 10:30, still a bit of time off of lunch, maybe? Good? Yeah.
For me, no problem. I finish.
If Juan is okay, it's okay. Good. Okay. So let's say we come back around 10:30. If you have any questions for Javier, please go have some lunch, coffee with him, and then ask questions. Thank you very much.